Hello. Okay, here we are. Hello, this is Ricardo from the Construct.
And I'm Rodrigo.
And today we are here in order to see the presentation of Bladimir Bacca, who is a student of ROS at the Construct Academy. And he's going to present his project he has done while studying the ROS Basics in 5 days course. Hello, Bladimir. How are you doing?
Hello there. Hello, everybody. It's very nice to be here.
Are you ready to do your presentation?
Yep.
Okay, so you will be able to do your presentation and you have between 15 and 20 minutes to do it. You can use also your project, your project that you have done while doing your course. And also you can connect to the real robot remotely and show to the audience what is your project about. After your presentation, Rodrigo and I will do some questions to you in order to check that you really have mastered this course.
Okie dokie. Well, let's start to share my screen. Just to be sure, you can see my screen.
Yes.
Yeah. Okay.
Wait a second. It's still loading. Let me see. Okay, let me see. Wait, we cannot see your screen. Okay, wait a second. There is a problem in the transmission. Your screen is correctly shared, but it's problem here. Just a second. There it goes.
There we go.
Okie dokie. Well, let's start with locating the robot, just in case something happens. Okie dokie. Okay. Well, let's figure out what is the right. Okie dokie. That's the right command. Well, first of all, I want to sorry, I want to show basically the main code. Usually, my strategy to develop code is starting from the top to the bottom, and in doing so, I like to share with you the launch files, the main launch files, and you can see that in the first part of this launch file basically loads the action server and then the ROS program that I developed. Okay, okay. Well, um, like as we are working with the actions in ROS, this is the Odom record action file, which is obviously separated in three main parts. The first part is the goal, the second part is the result, and the third part is the feedback. After you make the proper changes in the CMake list txt and package XML files, you have to compile this action, because obviously this is a custom action before use it. Then the the following the main program, basically I call it wall follower PI. In the wall follower PI, the the basic steps which are extracted from the course in some of the examples of the course, you can see that an action client basically is starting up. Then you have to wait for the connection with the action server. The goal is basically built and sent to the action server. Here, basically, you can get the state, but After that, you have to, in this case, you have to perform the subscriptions to the laser scan and to instantiate the publisher in order to send commands to the robot. Here in the laser scan, the callback, which is my LRF callback, is a method which can you see here, and it is basically this callback deal with all the task of following the wall. Okay, okay. Then after that, basically in this while, you consult or request the state of the action server and basically sleep. Then two tasks are concurrently performed, which is the taking the odometry of the robot on one hand, and on the other hand, basically is uh, following the wall. After that, you have to stop the robot theoretically and finally show the results. Then this is the main program. The action server, which responds with the action commands in the ROS program, is this file. Basically, it's a Python standard ROS program. And in this program, I instantiate an object of action Odom class. The action Odom class is contained here in this same file. You can observe that in the constructor, other objects are instantiated. One of them is the Odom record results and the Odom record feedback, which are compiled before when you make the compilation of the project. And the odometry record, which is a class I developed to deal with all the odometry data. Then the action server is started, and obviously the goal callback is done all the work with the action server. This work with the action server is performed until the lab around the environment is done. Well, what kind of actions are performed here? Firstly, you have to basically pay attention if any cancellation event is requested. Then the points of the odometry are saved. You in this method, basically you retrieve from the odometry class the previous and the current position in order to calculate basically the distance to the origin. And in order to see how it's going on, uh, print this information, then build basically the feedback and publish the feedback. Finally, you sleep for a second, which is the one of the requirements of the project. At the end, when the lab is finished, the result is built and published, obviously, in the corresponding topic. Well, this is the action server. Now, the odometric class, which deals with all of the odometry data, is shown here. Here, in the constructor, a subscription is performed to the ODOM topic to get the odometry, and obviously other internal variables of the class. Here we can find basically some methods as the callback of the odometry, which performs all the task in getting the data and computing the distances and everything. The first part you can see here, and basically you get from the message the position of the robot and the orientation of the robot. You save the origin position of the robot. Then the current pose and the previous pose are um, uh, initialize it, and the distance relative with the previous post is computed. This is basically a relative distance, and this relative distance is summed up in order to show how many meters the the robot traveled so far. Other methods involve basically retrieve some internal variables like the previous and current positions, the uh, save the odometry points, get some distance, that get the points, get the distance to the origin, which is a different distance, and this is important. Basically, this is the method uh, which I use in order to detect if I reach the original position. But it is not a point, but a region, a circular region. And using that, basically, if the robot approaches to any positions within this circle, it is assumed that the robot basically finished the lap. That is all. Then, oops. Okay, okay. Let's start the the demonstration. Well, I have to initialize another shell here.
As you
Let's,
can see, Vladimir, we have included
yep,
a second camera
yep,
in the lab in the meantime that you were preparing your presentation. So I hope that this is not confusing you. Everything is correct. So you have now
uh,
two different positions of the same robot.
or the same robot. Yeah,
Mhm.
don't, I realized that.
Yeah.
Okay.
It was very confusing at the beginning, but
At the beginning, yeah, I can
I,
imagine. Sorry for that.
okay, okay. Well, let's start basically the the pro the main program, and you can see this when it's starting of the client, waiting for the action server, listen the messages, and it starts to following with basically following the world. You can see that the message published
Nice, nice,
here
nice.
is the distance to the origin and the current positions. But if we need to see the topics generated here, entonces, then ROS topic list. When you list the current topics, you can see that the actions previously compiled. Here we can see the ROS topic about the feedback, and the feedback is continuously updated with the current distance traveled so far. If we start up another shell, you can see obviously the same topics, but here we desire to see the result. Obviously, the result is just published at the end of the lab. In this case, it's empty, but the 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 total distance traveled so far is updated in the feedback. And this is obviously the main program, which is printed some message in the console. I don't know if while the robot reaches the reaches the the original position, you have any questions.
Impressive presentation, and your robot is still moving around there. Can you make us a favor to the audience? Can you enlarge a little bit the window that shows the real robot a little bit
Uh,
so we can see better the robot?
yeah,
Ah,
that is
great. Great.
the
Oh,
robot.
yeah, we should see on the second camera on the other side. This other second camera has to be better oriented, but we'll do it. But we can see very clear on the camera number one, the robot
Yeah, yeah,
and how it has turned on on the corners for that.
Corners, yeah.
And then if we keep moving, if I have correctly understood, then we are going to see the robot reaching the final position and then getting the final action result, right? On the topic that you have posted in one of the terminals.
Yeah, and in theory, the robot, well, should be stopped. In Gazebo, it works.
After one
I
lap?
don't know how.
Uh-huh.
I don't know how. Why in the real robot it doesn't happen.
It doesn't happen. Okay.
No.
Okay, yeah, QP. Oh, something happened with the camera there.
I don't know what happened.
Okay.
What?
Oh, so it was some kind of glitch of the...
No, it actually resets itself every certain amount of time to avoid losing the signal. But there you go.
Okay.
There's the other one.
There was the Okay. Okay, but it's awesome that it's not... So that is doing it. It's doing it. Yeah, it's about to reach.
Here is the end of the... for that reason, I performed this shell in order to really stop the robot avoiding to crash into the walls.
Okay. Okay.
Because
Okay. Then about this point that you mentioned that in real robot doesn't stop.
doesn't stop. Yeah, in fact, you can... sorry, move this. At the end of the program, I even publish two stopping commands, but I don't know why this not are performed at the end.
Okay, are you sure that this condition is being executed? So when are those stopping commands being executed? When happened what?
When basically you get off of the while.
Okay.
And get off the while when you basically reach the original.
The zone. Okay.
Yeah.
And how do you measure that it has reached the previous location, the starting location? So it has done a complete...
Starting location, basically, I mentioned it before, but here is the...
Yeah, we saw it, but just to clarify, and maybe we can find the error together.
Yeah. That is basically, I built virtual circles in the original position. And that circle is a radius of basically 25 centimeters. And if the robot is close to that original position within a radius of 25 centimeters, basically it stops.
Yeah, you consider that it has reached the original position, more or less.
Yeah, more or less, exactly. Because returning to the exact same point is difficult at this level, obviously.
Yeah.
In Islam applications, you can do the loop closing and everything, and those methods, but here is not the point.
Very, very good idea. This one. How did you get that idea about creating this area of?
Well, we use it. We often use it in my university to deal with these closed paths.
Okay.
In my work with my students.
Okay.
It's a really easy idea to define if you reach the original position.
Exactly.
Or more or less.
Exactly. No, yeah, that's very cool, very good. And then one thing that comes to my mind that maybe is the reason is because the odometry maybe has been drifting too much.
Yeah.
So maybe even this area of 0.25 is not enough for detecting as the same. You should, in order to identify this, you should plot the values of the odometry. Where are you storing the values of the odometry? In here, exactly on that. odometry record class?
Yeah. In the odometry record class, I have basically here. This is the method which with I command the odometry point is saved in this, which is basically a vector of odd objects.
Okay, I see. And those three components, I can see that you have odom curve pose 0, 1, and 2. Those correspond to what exactly?
Those correspond to the X position, Y position, and the orientation of the
Okay, great.
They basically append at the end of the array.
Exactly.
Which is called odom points.
Odom points. So odom points is the one that contains at the end of the whole sequence. It contains all the points that have been moving around the robot. So maybe for the future, in case that you want to practice more and so on, you can plot those points at the end in an XY axis, and then you will see what happened with your trajectory. Maybe there is a big error in the odometry. I don't know. So I'm just guessing a possible solution. Or if it is not, if there is no error, then you have some error in your logic of checking for the position when you are comparing the 25 centimeters. Are you doing the square root of all that?
No, I didn't do that. I didn't do that. But it is a nice idea because basically the robot obviously is navigating using odometry and not the sensor.
Yes,
and
exactly.
For that reason, obviously there is a drift
Yeah.
on the trajectory.
And that explains why there's in Gazebo it's working correctly because there's no drift in there.
Maybe in Gazebo works exactly because it's more exact. It's more exact, and in reality, it's not so exact. Maybe that. Okay, one question more.
You tell me.
It's about the so how do you get the theta, the orientation of the robot?
The theta.
Yeah.
The theta is obtained from here. Well, basically the callback of the audiometry topic, you can retrieve from the data the orientation, but this orientation basically is a quaternion. And you have to use the Euler from quaternion method to translate basically the quaternion to the roll, pitch, and yaw angles, which is the Euler angles.
Your Euler, yeah.
And take just the yaw angle.
Okay, exactly. And that is the theta of the robot. Exactly. Very good. Very good. So I can see that you know what you were doing very well.
Thank you.
Very good. Thank you. Any other question? There you go.
No, I just want to make a comment about that. The way you're recording the odometry and it's showing up on the terminal. That's really nice, and it's like really clear on what the robot is doing. Yeah, that one, the odometry, that total is basically like the linear, like how long it's been going around, right? So you're recording the XY displacement between points.
Yeah, at my experience, basically printing message, printing everything in the screen or through the serial port or whatever is basically the best debugging tool.
Yeah, it's always helpful.
You can reach.
Okay, but then for robotics, you have to start thinking the other way, because now in this case is, let's say, quite simple. Let's say, okay, so it's the beginners of this, but then it becomes a lot more complex, and then for that you need to get used to the graphical tools that ROS provides, like for example the RBIS. RBIS. Then, for example, in RBIS you can plot all the points that you are moving around, and then at the end you can point all the odometry values, and then you can see the trajectory that it has done the robot. So also, and then it's quite easy. Right? It's not difficult to do that.
Yeah.
So I recommend you that you start practicing with it.
Practicing with that. Okay. I will.
Okay, great. And then related to your, so we can see that you know what you were doing, and so that the project that you did your project, and that you decided some of the options. For example, this one about detecting the final location, you decided yourself. So it was not on the project necessarily, but you decided to do it, and it's very cool that you have integrated that. But I would like to ask you, which was the part that you struggled the most in order to complete this project? What was the most difficult part?
The more difficult part was basically here. Where is the here in the action server, because when you do when you run this code in the simulation, that environment is built using Python 3. But here with the real robot, I didn't realize that it is just Python 2. And I have a problem which runs for 2 weeks or more even, but it's a silly error. When I told you here, it sounds very stupid.
Okay, no worries. Here's the place for that.
Basically, this class, the odometry record class, which deals with the odometry data, do not instantiate this object robot odom. Basically, for this program, which is the action server, doesn't exist, and obviously it make my brains search about the about the answer. And I read in a blog of Python that you can see here the original import code. From the odometry record class, import odometry record, which is basically the name of the class. But this doesn't work. It works with that. Basically, import all
of them.
the objects that you can find in this file.
Okay.
After that, everything works perfectly.
Okay.
This is basically the most difficult
problem. Okay. But I think that this is not related to Python 2 or Python 3, because you are receiving just messages from the robot. So from the robot, you are not executing your code inside the robot. So your code is made on Python 3. Sorry, on Python 3, right? This one is Python 3. All this is Python 3, right? Yes. Then whatever it runs on the robot, it doesn't matter which Python it is installed in the robot, because it is just sending you topics. It's just sending you messages. So it's not related. I'm telling you just to clarify so you don't get confused about the reason of this problem. So this is not related to Python 2 or Python 3. Python 2 being on the robot and Python 3 on the development environment that you have here. Okay, so it cannot be. What it could be is that you need to import some extra data from the odometry record class that you need to use. So by only importing the odometry record, you were missing some other parts of the class that you need. So by doing this import star, you are importing everything from there. And this automatic record is a class that you have created, right?
Yeah, I have created. Yeah, but it's the only class in this file. There is not other classes in this file.
Okay.
The only one is the automatic record.
Okay. Oh, okay.
That is the
A strange thing.
the strange thing. Yeah.
Yes.
Because this is the only one class.
Yes, that's right. Oh, maybe because
Maybe instead of from class import the library, it could be just import the class. No.
yeah, it's the same. It's the same as
Yeah.
doing the asterisk also.
Mm-hmm.
Yeah.
Okay, very strange problem.
Yeah.
But very strange problem. But what I want you to understand is that, so I don't know why this, we should see the messages that you receive and so on. But what I can certify you, so make you clear, is that it's not because of the robot being executing Python 2. It's not because of that. Okay, so because you are, by using topics, you are detached of the system. Well, up to a certain point, okay? If the ROS distributions are very, very different, then it will not work because some messages they are not defined, doesn't exist, and so on. Yeah, in this case, it's Python 3. Should be Python 3. What? No. Wait a second. Why? This is not.
That is the reason, because I realized that the versions of the Python versions of this ROS project is different for that in the simulation with Gazebo.
Okay.
I run this command, and for that reason I search about what happened in the syntax of importing things or importing classes from other files between the Python 2 and Python 3.
Vladimir.
And that's oriented me to this kind of imports instead of the comment.
Vladimir, let me just ask you, what if you click on that I on the bottom where it says Roblox Turtlebot 3, which is your ROSject, when you click on that I, what distribution is that? That's ROS Melodic.
Melodic.
Okay. Okay, so this is actually a ROSject that is not the one that was forked from the course, which is a noetic ROSject. Maybe this is an issue on our side, and we'll take a look at it.
Yeah, maybe, yes.
But maybe it has to do something with it, because noetic comes with Python 3. And this is melodic, and that's why it's showing up as Python 2. So maybe that was an issue there, and we'll take a look at it.
Yeah.
Yes, exactly. So you are running, your ROSject is running on ROS Melodic.
Yeah, okay. But the ROSject was created automatically when I was doing the course, and then I don't know.
Something happened there.
A change in the
Yes. Exactly. Yeah. Maybe it's in our side that we didn't provide you with the proper base, with the proper noetic. Okay. So, but then in any case, everything is
it's in Python
working.
2. Everything here is in Python 2. Yeah.
Yes, exactly. So everything is working, and you demonstrated that it works in the real robot now in real time. So no video. Real execution, and also you answer correctly the questions, demonstrating that you know the subject. So so you are going to have your certificate for sure. We are going to issue your score finally on the platform, so you will be able to see it and see your certificate that you can show on LinkedIn, of course.
Thank you very much.
Congratulations, Vladimir. It was really nice project.
Congratulations. No, not that one.
That was the wrong one.
Button.
I apologize.
Not that one. Down. Yeah.
Yeah.
That's a one.
Rookie mistake. I apologize.
Not laughing at you is.
Congratulations, Vladimir. That was a really impressive project.
Thank you. Thank you for your time and thank you for the platform because I really engage me to learn about ROS and even I'm doing the second course of the learning path.
That's great to hear.
Perfect.
Yep.
Perfect. Then, let me see here because maybe we didn't see some of the parts. So that's a problem in Zoom. Okay.
Do you want to stop sharing my screen?
No. Yes, please. Yes.
Okie dokie.
There it is.
There is it.
Yes. Okay. So here we have the. So thank you very much, Vladimir. Thank you.
Thank you. Thank you. See you next time.
Exactly.
All right. Thank you.
And to
Bye
all
bye.
the people over there listening and watching this video, so this guy, like Vladimir, it could be you. So you can start mastering ROS by learning the construct. Let me show you here by the construct. If you visit our academy, you can learn a lot. You can practice with those remote robots like Vladimir and also get your certificates if you demonstrate that you have acquired the knowledge, not just by watching some videos and so on, but demonstrate in real time, in real life that you know that. So visit our website. It's beneath here on the comments below. And see you on the next presentation with the next student.
Bye-bye, everyone.
Bye bye.
Bye-bye, Vladimir.